In this section, we're going to be solving systems of equations. And for the first video, we're going to talk about solving two equations in two variables. Now, previously, when we talked about this, we talked about solving the system of equations by graphing. In this set of problems, we're going to solve using a method called elimination, or it's sometimes called the addition method. Okay, so here's the main idea. When we have a system of two equations, we can do a couple of different things and still have the same solution. We can multiply an equation by anything that we want to, as long as we multiply by both sides, any constant that we want to. And we can add the two equations together as long as the x's, the y's, and the equal signs are all lined up. So the way it's written right now, it would not be very helpful to add these two equations together. I'm going to do this in red, and I'm going to do it very quickly because it's not helpful, because none of our variables add up to 0. 3x plus 2x makes a 5x. 4y minus 3y, negative 4y, sorry, minus 3y makes a negative 7y. And 7 minus 1 makes 6, which I don't care so much about because the 5x wasn't a 0x and the 7y wasn't a 0y. So we're going to try to find a number, or sometimes two, one that we multiply by the one equation and or the other equation to make the x's or the y's add to 0. So I'm going to choose to make the x's add up to 0, the 3x and the 2x. And I can't change the 3 into a 2 or a 2 into a 3, but I can change each one of them into a 6. So here's what I'll do. I'll multiply, if I multiply the top 3x by 2 and the bottom 2x by 3, that'll make each one of them a 6x. Doesn't quite add to 0 yet. I need to make one of them a negative. So I'll choose the negative 3 for the bottom equation. Okay. Now I can't just multiply the x portion by the 2 and the x portion by the 3. So I'm going to multiply both sides of the top equation by a 2, turning that equation into 6x minus 8y equals 14. If you graphed, by the way, 6x minus 8y equals 14, and you graphed the original 3x minus 4y equals 7, you get exactly the same graph. So this is the same equation that we're looking at, just multiplied by a 2. And the bottom equation, I'm going to multiply by negative 3, both sides. So this turns into negative 6x, negative 3 and negative 3y makes a positive 9y, and negative 1 times negative 3 is 3. Now, when we add these two equations together, watch what happens. 6x minus 6x is 0. Negative 9y, negative 8y plus 9y is 1y. And 14 plus 3 is 17. So we have one part of our solution, y is equal to 17. Now, in order to find the x part of the solution, because we should always get an x and a y for our answer, in order to find that x, there are two different things that we could do. We could plug y equals 17 into any xy equation. So maybe 3x minus 4y equals 7, or 2x minus 3y equals negative 1, or even one of the red equations, 6x minus 8y equals 14. I'd like to practice with you doing the elimination one more time, so we could also use elimination one more time. And instead of making the x's go away to 0, we could make the y's add up to 0. I think in this system of equations, it would be easier to plug in y equals 17 into one of our equations. So let's choose the top one, 3x minus 4y equals 7, and we're going to plug in y equals 17. That'd be 3x minus 4 times 17 equals 7. So 3x minus, what is that, 68 equals 7. Adding the 68 to both sides, we get 3x equals 75, and dividing by 3, x equals 25. So our system of equations has a solution at the ordered pair x equals 25 and y equals 17. Pretty much every single time we write the answer to a system of equations, we write it in ordered pair, or in the bigger problems, ordered triple form, where the x come first and the y come second, to remind us that we have an intersection point for those two equations. Let's do one or two more examples. All right. For this next set of equations, let's make them a little bit uglier. Let's solve negative x over 5 plus y over 2 equals 1 over 10, combined with x over 2 plus 7 over 6y equals negative 1/3. Now, at first glance, those look pretty terrible, but what is wonderful about these is we have an equation for each one of them, which, as long as we have an equal sign in any form here, we can clear away our fractions, which is exactly what we're going to do here. So remember, when you're clearing away fractions, what you're doing is finding the least common denominator for each equation. So for the top equation, looks like the LCD between 5, 2, and 10 is 10. So I'm going to multiply both sides of my equation by 10, or maybe 10 over 1. And when we reduce that, 10 over 5 is 2. That's negative 2x. 2 goes into 10 5 times, plus 5y. And 10 over 10 is 1 equals 1. And in the bottom equation, let's see, between a 2, a 6, and a 3, the LCD there is 6. So multiply both sides of our equation by 6, or 6 over 1, and reduce. 2 goes into 6 3 times, so this will be 3x. 6 goes into 6 once, so that will be a plus 7y. And 3 goes into 6 twice, leaving us with a negative 2. Great. Now we have a much better looking system of equations to solve, but it'll give us the same exact solution as the original one with the fractions. So, same idea that we did in the last problem. Let's try to get the x's to add to 0, simply because 2 and 3 look a little easier to deal with than 5 and 7. Okay, so just like in the last problem, I can turn 2 and 3 into 6's, both of them. I want to make sure that one's a positive and one's a negative, which is great because they already are different signs. So I'll multiply the top equation by a 3 and the bottom equation by a 2, and that should do it. So multiplying the top equation by 3 gives me negative 6x plus 15y equals 3. And multiplying by the bottom equation by a 2 makes 6x plus 14y equals negative 4. And this is perfect. When we add these together, the negative 6 and the positive 6x cancel. 15y and 14y, is 29y. And 3 plus negative 4 is negative 1. So our y is an unappetizing negative 1 over 29. Now remember, in the previous problem I said we have two choices. We can take that y value and plug it back into any xy equation. I'm not excited about doing that. Or we can do elimination again, and instead of making the x's cancel to 0, this time try to make the y's cancel to 0. So I'm going to do that second way here. So I'm going to go back and start with the cleared fraction version, negative 2x plus 5y equals 1, and 3x plus 7y equals negative 2. But instead of multiplying to make the x's disappear to 0, I'm going to make the y's. So 5 and 7, I can turn each one of those into a 35. I can multiply the top equation by 7s and the bottom equation by 5s. One problem right away is they're both going to be a positive 35, so I'm going to pick the 7 to be negative, just so one is negative 35, the other's positive 35. And I think I'm going to write these results down here. So this will be negative 7 times the top equation gives 14x minus 35y equals negative 7. And the bottom equation, 15x plus 35y equals negative 10. We add these together. 14x and 15x makes 29x. Thankfully, at least the 35y's cancel. One's negative and one's positive. And that's equal to, let's see, negative 10 and negative 7 makes negative 17. So solving for x, we have negative 17 over 29. What I won't do to avoid common denominators. So our answer in alphabetical order, x is negative 17 over 29. Y is negative 1 over 29. Let's do one more example. All right, last example. Let's solve 2x minus 6y equals 1 and negative 5x plus 15y equals negative 7. Okay, fortunately no fractions to start, unlike the last example, so let's just get started by making the x's try to go add to 0. So we'll do that by, let's see, 2x and negative 5x. I love that they're opposite signs already. So let's turn them both into a 10. I'll multiply the top by 5 and the bottom by 2. Okay, so that would make the top equation 10x minus 30y equals 5. And the bottom equation, negative 10x plus 30y equals negative 14. Okay, when I add these together, I am delighted that the x's cancel to 0. A little alarmed that the y's also, negative 30y and positive 30y, also add to 0. And okay, 5 minus 14 is negative 9. But all of my x's and all of my y's went away, making 0 equals negative 9 without any x's or y's, my result. Well, you're probably not surprised to know that this means that we have no solution. But since we spoke a little bit in the very first video about graphical interpretation, what that means is if we were to graph each of these lines, we would have no intersection point. So these would represent parallel lines if we were to graph each one of them. If we were to solve these system of equations and say we were to get something instead, like say we got negative 9 equals negative 9, then we would have the same line. You might be tempted, algebra experts, to say that this means we have all real numbers as solutions, but what this really means is that we have just infinite intersection points or infinite solutions. Okay, for this example, however, since we got something that was not true, 0 does not equal negative 9, we have no solution.